Yeah, so what we are going to see today is very simple stuff, some basic math and a little bit of theory. So we'll start with particle in a 1D potential well. So this is based on the concepts we saw in the previous lecture. So we studied something called the wave function, which is a complex function which gives you complete information about a particle. So it is a function from which you can extract the particle's position, momentum, energy, any observable quantity that you need by performing specific mathematical operations. So in the previous lectures, we saw how to extract these quantities from the wave function. We didn't see what the actual wave function looks like. So if you had attended the previous lecture or if you had seen the videos of that lecture, you would have noticed I emphasize this point often. We're not going to look at the actual expansion of the wave function. We're not going to see what the function expression actually is. We'll only see, given the value of the wave function, how are we going to extract whatever quantity we want. So in this lecture we are going to look at the actual expansion of the wave function for given conditions. So what are those conditions? A one-dimensional potential well. So basically it is like you have a small particle trapped inside an infinitely deep potential well. What do you mean by potential well? It is like a pit you dig into the soil, infinite depth. So the depth or height of the pit is infinite and the width is L, let's say 0 to L, and the particle can only exist between the 0 and L dimensions. It cannot exist to the left of 0 or to the right of L. Why so? Because the potential is infinite for all x less than equal to 0 and for all x greater than equal to L. And a particle cannot exist at infinite potential. It needs to exist at a finite potential only. So we have this big well or pit kind of thing. Its depth is infinite. It has a width of L units. To the left of 0 or to the right of L, the potential is infinite, so my particle will not exist there. Between 0 and L, my potential is 0. So by particle, I mean a charge, electron, basically any body that carries a charge. So I know that my particle is going to exist somewhere between this 0 and L. This is what we know so far. Okay. So moving on, this is the symbol for the wave function, and in the previous lecture we saw that the modulus squared of the wave function gives you the probability of finding a particle at any specific location. So we know that the probability of finding the particle at any place less than equal to 0 or greater than equal to L is 0, and within the space 0 to L the probability is 1, because we just discussed 0 to L is the only area within which the particle can exist. So this is the knowledge we have so far. Based on this, we are going to try and find out an expression for this wave function psi. So this is the time independent Schrodinger's equation for one dimension, and just to reiterate, we are talking about a one dimensional potential well. So it only has this length. We don't talk about a breadth, width and so on. So because we are talking about one dimension, we take the one dimensional time independent Schrodinger's equation. Why time independent? Because the potential is constant. It is either infinity to the left of 0 and to the right of L, or it is 0 potential between 0 and L. So the potential is not varying with time in any sense. So we take the one dimensional time independent Schrodinger's equation. This is the equation. How did this come about? We derived in the previous lecture. So we take this equation and we multiply with 2m by h cross squared. We get this equation, and then we bring e to the left side and we just do some basic regrouping of terms. You're bringing everything to the left side and making the right hand side equal to 0. You get this second derivative of phi of x with respect to x plus 2m by h cross squared times E minus V of x times psi of x equals 0. Here psi of x is the wave function, m is the mass of the electron, h cross equals h divided by 2 pi, where h is your Planck's constant and pi is 3.14. So h cross is just another constant. E is the total energy of the particle, V is the potential energy. So we have this equation now. And for an electron inside the well, potential is 0. So we just discussed the electron can exist only between 0 and L, and at any point between 0 and L, the potential V is going to be 0. So this V term becomes equal to 0. So we have second derivative of psi of x plus 2m by h cross whole squared into E psi of x equals 0. This is what we have now. So we have this equation now. So now what we do is we assume k squared equals 2m by h cross squared E. So we just taking this entire quantity and assigning it to a variable called k squared. And why we do that we'll come to know when we go to the further slides. So right now we just assume k squared equals 2me divided by h cross squared. Now like I said, h cross is nothing but h by 2 pi. So when you substitute that, we get k squared is equal to 8 pi squared me divided by h squared. So what did we do? We just assumed k square equals 2me by h cross squared, and then in place of h cross we put h by 2 pi. So we get k squared equals 8 pi squared me by h squared. So coming back to this equation, second derivative of psi of x with respect to x plus 2m by h cross squared E times psi of x equal to 0, and this 2m by h cross squared E is exactly what we took as k squared. So substituting that, what equation do we have now? Second derivative of psi of x plus k squared times psi of x equals 0. This is the equation we have now. And and like I said, the whole objective of this exercise is to find out an expansion for the wave function. We want to find out an expression which satisfies psi of x, and whatever expression we take, it must satisfy this equation. So physicists and mathematicians, they took different types of expressions and they substituted that for psi of x and they tried solving, and only an expression of this form was found to satisfy this equation. So when you take any other function of x, like something like e to the power x or a sin x, a sin x is here, not a sin x, but e to the power x or x squared, some polynomial, exponential, something like that, log x, something like that, it did not satisfy this equation. Only an expression of the form a sin kx plus b cos kx was found to satisfy this condition. Second derivative of the function plus k squared times the function equals 0. So now we know what our psi of x looks like, a sin kx plus b cos kx. So we just need to find out the values of a and b. So we have this, and then using some other prior knowledge we have, we'll try to find out what the values of a and b are. So once we find out the values of a and b, we got our expression for psi of x.